You are watching one of a series of videos giving an introduction to OrcaFlex. The first 4 of these videos, which we've called the fundamentals, are those that we would regard as prerequisites for looking at any of the other subsequent topics. If you are already familiar with these fundamentals, you may want to pick and choose the subsequent videos you watch based on your area of interest. If you're a complete beginner with OrcaFlex, I would strongly encourage you to watch the full series in order, as this will give you a good basic overview of the program, how to navigate it, and where to access and input data. It goes without saying that the quality of any OrcaFlex analysis is only as good as the quality of the input data, and that, of course, relies on the skill and experience of you, the user. These videos will help you to learn how to use OrcaFlex as one of your analysis tools, and I do hope that you find them educational and maybe even a little bit enjoyable too. The focus of this next session will be the OrcaFlex objects. OrcaFlex is made up of 9 modular building blocks or objects. While later videos will look at the objects in detail, you will now be introduced to each of them, looking at their application, the types of data input needed, and how they can form part of a full model. The objects available are the vessel, the line, the 6D buoy, the 3D buoy, the winch, the link, the shape, the constraint, and the turbine. The objects are named based on their primary application, although it's important not to let this limit your thinking. For example, buoys are not just used for modelling floating buoys, but can also be used to apply mass at a specific point to represent anything from a crane hook to a subsea manifold. Likewise, the winch isn't just for modelling winches, but can be used when something needs to dynamically change in length. So, taking a look at the vessel object, this is typically used, as you might expect, to model things like ships, barges, large floating platforms, or, as in this case, FPSOs. However, it can more widely be used for anything that requires diffraction data associated with it, or something that needs to move in a prescribed direction over the course of a simulation. The vessel is a rigid body whose motion can be determined by the user in a number of ways, including response amplitude operators, or RAOs for the 6 degrees of freedom, first-order wave-load RAOs and second-order wave-drift QTFs, and it can also be driven around the sea surface with user-specified velocities and headings. The RAOs and QTFs are imported from a diffraction analysis program, an example of which is OrcaWave, which is bundled as part of the OrcaFlex license. This can also provide the data for creating the wireframe and the shaded graphics drawings of the vessel. Next up is the line. This is a flexible linear element which uses a lumped mass model to represent things like pipes, flexible hoses, cables and mooring lines. Its mass and hydrodynamic properties are lumped at nodes, which are connected by straight massless segments. The length of the segments, and therefore the quantity of the nodes, are decided by the user. The greater the number of nodes, the more accurate the line representation, but at the expense of simulation time and file size. The line properties can vary along its length. This line, for example, has 3 sections. The first and the last are a heavy line type, and the centre section is buoyant. And when we run a static analysis, we can see the centre section of the line is lifted up by that buoyant line type. The line ends can be fixed or free, or connected to other objects in a model, and ends can also be disconnected during the course of a simulation. Take, for example, this right-hand end of this line, which is connected to a vessel, and partway through the simulation, that line end is released. The contents of a line can also be modelled, as can additional elements such as buoyancy modules, clump weights and drag chains, all of which are modelled as attachments. We'll move on now to take a brief look at the two buoy objects. Note that although they are called buoys, they do not need to be buoyant. You set the level of buoyancy by inputting a combination of mass and volume parameters. First up is the 3D buoy. This is a simple point body with only 3 translational degrees of freedom, and it is represented as a vertical stick in the 3D view. These are intended to be used to model objects where you need to introduce mass but where rotations can be regarded as insignificant, such as shackles or crane hooks. You can see that the data form is quite simple, and here are the mass and volume parameters for setting the level of buoyancy. Moving on to the 6D buoy, this has, as the name suggests, 6 degrees of freedom, so can rotate as well as translate. It is intended to be used in the drag and inertia regime in which Morrison's equation applies, i.e. its characteristic dimension should be smaller than the wavelength it experiences. There are a few different types available for different applications, but we'll go on to talk more about this in a later video. We move on now to the link object, which is a simple, straight, massless connection linking 2 objects in a model. This can be defined as a tether link, which acts much like an elastic band, taking tension but not compression, or a spring damper link, which can take both tension and compression. Next is the winch, which is a massless connection between 2 or more objects. The connection length, simulating payout or haul-in, can vary dynamically through either length control, where the winch wire length varies at a user-specified rate, or tension control, where a user-specified tension is applied to the winch wire. The winch can be a simple type or a detailed type, the latter providing options to input additional winch drive properties and inertia properties. The next object is the shape, which is available in a number of geometry options and types. The shape options on their own are quite simple, such as this cylinder, or the plane, or the cuboid block, or the curved plate, but these can be combined to create some quite complex compound shapes. They can be used as an elastic solid type to create physical boundaries for other objects. They can be used for trapped water areas which are shielded from the waves, such as moon pools, and they can also be used as drawing shapes, purely for visualization purposes. And there's a further type called the label, which is used for the purpose of adding text labels to the wireframe 3D view. We move on now to the constraint object. Whilst not very interesting to look at, it is after all just a set of axes in the 3D view, this is arguably the most versatile of OrcaFlex objects. It has no physical properties itself, but allows for the customizing of connections between other objects. It has 2 frames of reference, one connected to a parent object and the other connected to one or more child objects. It can allow degrees of freedom to be introduced between parent and child objects, or to have imposed motion defined. The constraint has a wide variety of potential applications, such as crane modelling, which uses a number of constraints chained together in series, wave energy converters, pipe lay stingers, jacket launch simulations, calm buoys, and turret moored FPSOs. Remember though that the constraint is so versatile there will be many use cases for it that we haven't even considered yet. In fact, when we first introduced constraints to our users in 2016, we demonstrated how a combination of calculated and imposed motion constraints could be used to create a bicycle model. The final object in the OrcaFlex suite is the turbine. This is used for modelling horizontal axis wind turbines and includes dedicated models for the generator, gearbox, hub and blades. The blade model is similar structurally to the line model, being a beam element split up into nodes and segments. It can be fixed or flexible to capture aeroelastic coupling effects, and the aerodynamic loads are captured using a blade element momentum, or BEM, method. The turbine object allows for a floating offshore wind turbine analysis to be performed entirely within OrcaFlex. So that's an introduction to all of the OrcaFlex objects. In the next video we'll look at how some of these can be combined as we begin to build an OrcaFlex model. Hopefully you'll have found this to be a useful introduction to the modelling objects available in OrcaFlex. The next video in the series will look at creating a data file.